Welcome to week 6. This is the first lecture of week 6. This is actually a continuation of what we have studied in week 5. In week 5, we have mostly studied the shear flow in thin wall cross section beam due to applied shear forces. So, we had applied shear forces Sx and Sy and found out the shear flow in the cross section due to these shear forces. We have solved several examples which included a thin wall C section, thin wall I section and circular sections and so on. In this week, we will move on to finding the shear flow in thin wall cross section beam due to shear forces, but what is going to change this week is that instead of open cross section, we are going to deal with closed cross section beam. So, the new thing that is coming into picture is this closed cross section beam. So, this figure shows the closed thin wall cross section. So, this shows the thin walled closed cross section of a beam, where the black line is the thin wall of the cross section. Let us assume that the cross section has a thickness T, which is small compared to the other dimension of the cross section. C is the centroid and x and y are the centroidal axis in the plane of the cross section. Now, Sx and Sy are the shear forces applied in x and y direction. Now, if we want to find out the shear flow, we have done in the earlier lecture, we want to find out shear flow Qs in this cross section as a function of S, where S is this coordinate. So, we have used this given expression to find out the shear flow in a closed cross section beam. We will be using the same formula to find out the shear flow in the closed cross section beam as well, but the only difference is that here there would be an issue with finding out Q0. So, in an open cross section beam like that of a I section or a C section or a jet section, there were certain points on the beam where there were 0 shear flow. So, all this point had 0 shear flow, because this were on the beam surfaces and that they were equal to 0. So, we had seen all these points were 0. So, we could start from any of this point, and for this point we could have taken Q0 to be 0 and we have solved the problem rather easily. But if you see a closed cross section beam, there would be no such point on the free surface of the beam, and therefore, we will not have a starting point where the shear flow is 0 and we can calculate the shear flow in the remaining portion of the beam starting from that point. So, now comes the question that how are we going to then handle the shear flow in closed cross section beam. So, in order to now, what we have to do is that we have to assume at any arbitrary point P, this is an arbitrary point, we will assume, here we will assume that Q is equal to Q 0, where Q 0 is unknown. And starting from this point, we will find out Qs in the entire cross section of the beam. Now, all the Qs that we find out will have a factor Q 0 there. Now, that Q, so which will be unknown and will be hanging there as an unknown, and we have to find out this Q 0 later. Now, how do we find out Q 0? So, let me write it down, that for a closed cross section thin wall beam, for a closed instead of consider, we will say we assume so this is step 1. The next step is that so the next step, or the step 2, is to find out Qs in the cross section using equation 1, but this evaluated Qs will have Q 0 in the expression, which will be unknown. Now, the third step comes into picture. So, in the third step, we will assume that the shear forces are passing through the shear center of the cross section. Even if they are not passing through the shear center, we will assume that the shear forces are passing through the shear center of the cross section. So, let us assume So, once we assume that, then we can say therefore, the torsion due to the shear forces therefore, the torsion due to this shear forces are going to be 0, because we have assumed that the shear forces are going to pass through the passing through the shear center of the cross section. And as we have discussed earlier, if the shear forces passes through the shear center, the net torsional moment on the cross section is going to be 0. So, since there is no torsion, so the fourth step says, as there is no torsion, in the cross section, we can say that theta, or rate of angle of twist, is, that is theta, has to be equal to 0, because there is no torsional moment. If theta is equal to 0, then using Bred-Pathos theorem, we can say that tau ds is going to be 2 g a theta. Now, in this expression, theta is equal to 0, since there is no torsional moment. Okay. So, if this is equal to 0, therefore, we can say that tau ds is equal to 0. Now, tau ds can actually be written as qs by ts if we have a varying thickness into ds is equal to 0. So, therefore, we are going to use this expression to find q0. So, we have got an additional equation. In this equation, we will substitute the value of qs. Now, we have in the values of qs, we have an unknown q0. Now, using this expression, we can find out q0, and thereby we can get the complete shear flow distribution in the cross section due to the shear forces. Now, the next question is that what will happen? We have assumed that the shear forces are passing through the shear center. Now, what will happen if the shear forces are not passing through the shear center? It will not pose much of an issue, because if the shear forces does not pass through the shear center, we can always make up an equivalent force system where the shear forces will pass through the shear center and there would be an additional torsional moment about the shear center. So, we can always find out the shear flow due to this additional torsional moment and add or subtract it based on the sign convention with the shear flow from the shear forces and get the total shear force flow in the cross section. So, this is the methodology that we are going to follow to find out the shear flow in a closed cross section beam. Now, this theory that we have discussed is going to become far more clear as we try to solve an example. So, let us consider this example. So, this is a thin walled rectangular cross section. So, this is a Okay. So, so the dimensions are given in this form. So, this dimension is, so this is the centroid. So, this dimension is 60 t. This dimension is 48 t. This thickness is 2 t. This thickness is t. This thickness is t. And this thickness is 3 t. Now, we can see from the dimension that this rectangle is symmetric, or the cross section, the rectangular cross section is symmetric about x axis. So, because of this symmetry, we know that I x y is going to be 0 for this cross section. Now, the problem statement says that if a shear force F is applied through the shear center of the cross section. So, the problem statement says that a shear force F along y direction is applied through the shear center of the cross section. So, what does it say? That a shear force is applied through the shear center. A shear force F along y direction is applied through the shear center. So, this probably the shear center. We do not know the location of the shear center, but because of the symmetry we know that the shear center has to lie on the x axis, and therefore, let us assume that this is the shear center and the force F, shear force F is acting through the shear center. Now, we need to find out the shear flow in the cross section. Now, this is what we have to do. We need to find out the shear flow in the cross section. That's the problem statement. Now, we know from our previous slide that QS, I'm just writing this equation again because we will be using this a lot. So, this is for ready reference. So, this is equation 1. Now, let us see what will happen to this equation for our particular problem. So, for this equation I x y is equal to 0, because it is symmetric. It has a symmetry about x axis. Now, we also know that S y is f, that is given. So, S x is equal to 0. So, therefore, this equation therefore just boils down to minus S y by I y y by I x x So, this is all that we have. So, t is basically varying. So, this is going to be T s. So, t is a function of s, t is not uniform unlike most of the examples that we have solved. So, this is t y into t s. Now, let me substitute S y is f and then I have I x x left here and then 0 to s t s y t s. So, let me call it as equation 2. Therefore, we see that to find out the shear flow in this cross section, I just need to find out only one sectional property, that is I x x. So, before I can find out the sectional property I x x, because this cross section has an unsymmetry about y axis, we need to find out the centroid of the cross section. Which is C. I need to find this out. So, let me say that the centroidal distance is this one, which is y c. So, I need to find out y c. So, let us see how we can find out y c. So, y c is going to be the top portion, which is the top portion which is going to, so y c is of course, sorry. So, y c is of course 24, it is through the x axis. We need to find out, so this is of course 24 t, half of this. We need to find out x c. So, let me call this as x c. So, that is what we need to find out. So, we need to find out x c. So, let me find out what is x c. So, if we calculate x c by the conventional method, let us try to find out what is x c. So, this will have no contribution to x c. So, this portion, so let me name them as well. So, let me name them as 1, 2, 3 and 4. So, let me just substitute a certain number, so that we can refer to them as and when we need to refer them. So, let me call this as 1, this as 2, this as 3, this as 4. Now, when we are finding out x c, we can say that x c is going to be, because of portion 1 4, it is going to be 48 t into 3 t okay. So I'm not going to, so I have solved the problem earlier. I have taken this to be x c. So, this is x c. So, I am finding out x c from the web 1 4. So, therefore, x c is 48 into, so this is 48 into 3 t into 60 t. So, this is for 2 3 portion 2 3 plus I will have the top and bottom flange. I will have 2 into 60 t into t into 30 t divided by the total area, which is 2 into 60 t square plus 48 t into 3 t plus 48 t into 2 t. So, if we evaluate this, we will get this as 36 t. Therefore, SC is located as 36 t from the web 1 4. So, let me just clearly mention this. This is looking bit of cluttered. So, I have find out this is my XC, which is 36 t, and this is the remaining portion, which is 24 t. So, we have find out XC, the location of XC. Now, similarly, we need to find out IXX about the sectional property about the XS axis. So, if I find out the IXX, it is going to be 1/12 48 t whole cube into 3 t plus 1/12 plus so this is going to be 30 t minus 36 t, sorry. So, this is going to be 24 t whole square. So, if we evaluate this, this is going to turn up as 115,200 t cube. So, this is for flange, this is for flange 2 3, this is for web 2 3, this is for web 1 4, and this is for flanges 1 2 and 3 4. So, 1 2 and 3 4 is going to contribute in this form, and the other two are going to be contributing for this two, and this is the final IXX for the cross section. So, and XT is given as 36 t. So, we will carry on, this is a lengthy problem, we will be carrying on this problem further in the next lecture and will be solving the problem. Thank you.